Okay.
Okay, so it's recording now, and please go ahead.
Okay. Well, hi everyone. It's a pleasure to be speaking to you on this occasion. First, let me say that this is my first attempt at a Zoominar, so hopefully this goes as planned, and hopefully the audio and video are clear. So I'm Hussein Nassar. I'm from the University of Missouri. However, I'm not stranger to France. Let's say I did a lot of studies there. My undergrad, graduate, and PhD actually all in France. So I recognized a few of the names here, and it's a pleasure to be speaking to you all once more. So for today's talk, I thought I'd talk about two topics, both related to trusses with mechanisms. So a truss is, well, it's a truss. It's a frame with members and bonds connecting nodes that can move and deform. In particular, I'll be looking at some trusses with mechanisms. So these are trusses that have some soft modes and that can deform with minimum energy cost. I'm interested in a couple of phenomena that appear in such trusses. One is cloaking, hence the title of this presentation, and the other is the emergence of polarization in these trusses. I'm not sure if time will allow me to visit both of these topics in a sufficient manner, but let's see how things go. Okay, so let's start with perhaps the simplest of all trusses, a triangular truss. So whenever you see one of these blue lines, you could think of that as a bond or as a spring. And whenever two bonds meet, they meet at a hinge. For a triangular truss, well, hinges are not very useful, but what's important is that none of these bonds will transmit any couples. So don't think of them as beams, think of them more as struts or strings once more. So I'm interested in knowing, for such a truss, what's the relationship between stress, if you apply such forces, for instance, and then the deformation, and that is strain. So I apply a few stresses and I look at the strain, but I only do so from a macroscopic point of view. So I'm not interested in the detail of the stress field and neither in the detail of the strain field. I'm only interested in sort of the coarse or the overall or the effective or the macroscopic or the homogenized response of this truss. All of these are equivalent words for what I'd like to do here. Okay, so let's try to do that. So let's introduce a few notations. X will be the node where the node I'm looking at, and I'll introduce a few lattice vectors. You'll notice that all of the trusses I'll be talking about are periodic. So you can translate them in a couple of ways that will not change the structure. This is a limitation of of myself actually, because non-periodic structures come with their own set of complex, and I didn't want to deal with all of that, so I'll restrict myself to periodic systems. Okay, so given X, let's try to calculate the elongation of bond 1. That is the bond aligned with lattice vector R1, this vector here. So this is given by U at X plus R1. So this is X plus R1 is here. I take the displacement, U will be displacement all over the star, minus U of X and then I project that over one. So or dot product if you prefer. And then the hat over R1 means I normalized R1. And so this is the strain of the string R1. That's the elongation of bond 1. Fairly simple, very well. Let's assume that U is smoothly varying, slowly varying, and that comes from the hypothesis I just made, that I'm interested in macroscopic states of stress and strain. And so this can be Taylor expanded. I end up with the gradient of U applied to R1, and R1 here is now understood as a perturbation projected over hat R1. But R1 here, R1 there, that means that instead of this gradient of U, I can restrict myself to this symmetrized gradient, and that's what we call strain or infinitesimal strain. I can normalize the first R1 to get A, where A is a lattice constant, a lattice step. And I can now calculate the strain energy in that bond. I take the square of that and I multiply by some spring constant K over there. Okay, now I can calculate the strain energy density. So the difference between strain energy and strain energy density is simply division by the area of one unit cell. And I do that. I end up with the square root of 3 that comes from the height of one of these equilateral triangles, and then a square over there. Great, I have the strain energy. Now I can calculate the Lagrangian density of this lattice. And I do so by summing all of the strain energies. So I sum over J. J goes from 1 to 2 to 3. All of the bonds are either, let's say, homologous to 1, 2, or 3. And so it's enough to sum over 1, 2, 3. And that gives me Lagrangian density. This is strain energy. And then I subtract the kinetic energy. And kinetic energy is rather easy to deal with. It's mass density over 2 times velocity squared. Awesome. This allows me now to calculate stress, and stress is simply the derivative of the Lagrangian density with respect to the strain. And so I end up with a 2 that comes here, and I have this expression, this linear expression in terms of the infinitesimal strain that produces the macroscopic state of stress. Okay, nothing too fancy. Now I decide spice things up a little bit. So at each node, I embed now a mass of a finite size. And quickly I realized that this doesn't do much. I still have the same Lagrangian density. The bonds did not change orientation. Rotation of the masses is sort of irrelevant in this example. And so nothing interesting is happening there. And so I decide to rotate each of the masses by finite amount. And I end up with this lattice here. In the literature, you could see this lattice called hexachiral. That stands for hexagonal because the lattice is hexagonal. And then it's chiral because it has this chirality to it. That is, although it has some inversion symmetry, actually, it does not have any mirror symmetry. And so we call that chirality, and the lattice is chiral. And so we call it hexachiral. Anyway, let's try to figure out what's the Lagrangian density for that lattice. And I'm telling you, if we introduce these notations now, the lattice vectors are still the same, the R's, but now I need other names for the bonds because now the bonds and the lattice vectors are no longer aligned. Well, with these notations, I end up with this Lagrangian density. And here's why. Well, on one hand, the lattice vectors did not change, and these occupy this side of the strain tensor. And so I have Rj, I copy Rj. Now the bonds did change, and instead of Rj, now I have Bj. Okay, so instead of Rj, I have to plug in Bj. But now Rj and Bj do not match anymore. They're no longer parallel. And so I no longer have the right to use this symmetrized gradient. I no longer have the right to use the infinitesimal strain directly, and I have to resort back to the full displacement gradient. Okay? And with that Lagrangian in mind, I can now calculate stress. Again, I derive with respect to the gradient. And so the 2 here goes there. This is the same. And then I derive this expression with respect to the gradient, and I have a tensor product between B and R there. And that's the state of stress for this state of deformation. And now I look at this expression, and it has something weird to it. I don't know if you maybe if I give you a second, you can observe that there are two things that are not quite right about this expression. The first one is that, as I said, I no longer use the infinitesimal strain. I use the full gradient, but that means that infinitesimal rotations, if I plug in here an infinitesimal rotation, there's no reason why this product should vanish. And so infinitesimal rotations now do produce stress, something unusual, okay? The other thing is stress is no longer symmetric, because now if you transpose stress sigma, you end up, instead of B tensor product R, you end up with R tensor product V, and BR and RB have no reason to commute, have no reason to be equal. R and B have no reason to commute, okay? And so I have an asymmetric stress tensor. Both of these facts are unusual. However, they're not really two independent facts. They're one and the same, and here's why. If you look at Hooke's law, written like so, where AIJKL is the fourth order elasticity tensor, well, you can see that usually A has major symmetry. And so if you exchange IJ with KL, you end up with the same elasticity modulus. Okay, but if you assume that stress is symmetric so that you can commute I and J, well, then you can commute I and J here. But A has major symmetry, as I said, and that means that you can commute K and L. And actually, that means that if A is symmetric with respect to KL, that is symmetric with respect to strain, well, then because of this major symmetry that we admit here, and that comes actually from, well, from the Lagrangian density, from its existence. Anyway, if A has one of these symmetries, then it has the other one necessarily. And so these two facts, while unusual, they're one and only. And I'd like to understand what's happening here. How did this come to happen? Okay, so let's look with more care maybe at what we did. Usually stress symmetry is demonstrated using the equilibrium of torques or the equilibrium of angular momentum. That's called the second law of Euler. And the second law of Euler has a local form, something we call the second law of Cauchy. And if you look carefully, the second law of Cauchy does not tell you that stress is symmetric. It tells you that the asymmetric part of stress plus body torque produces zero. And what I need to explain is, where does this body torque comes from? Okay, so let's consider two of these masses from the lattice, and let's consider the forces applied to them. Let's say these two forces are equal and opposite. Well, then the bond will transmit this force, but the force transmitted by the bond needs to be parallel to the bond. That's our hypothesis, right? That bonds are like springs. They do not transmit moments, and therefore they can only apply forces parallel to their line of action. Okay, and so the force is transmitted there in that same direction as the bond, and that leaves me with a torque on each mass. This leaves me with a torque here, and similarly, by the same reasoning, I have another torque here. And so equilibrium does require there be a body torque. But I didn't apply a body torque, so where did that come from? Well, that comes from the hypothesis that there is no mass rotation. In my model so far, I didn't account for mass rotation. So I didn't allow for the masses to rotate to sort of relax the structure. And by not allowing masses to rotate, I created a body torque. And that body torque is what broke stress symmetry. Okay. But that hypothesis of no mass rotation is not physically sound, right? If you take that structure, you load it, masses will rotate and will relax the structure, will dissipate that body torque sort of, and will do ensure that stress becomes symmetric again. But is it really not physically sound to assume that masses cannot rotate? Let's see. I'll consider the same lattice. I made it a bit transparent. Hopefully you can still see it. if you need to, and I'll embed in each mass a resonator. Okay, so this is done very often in literature dealing with metamaterials. These structures that exhibit weird properties. Often these properties stem from resonators embedded within the structure. And for starters, I'll start with a similar structure, and I'll embed a resonator within each mass. So now the blue stuff is still just springs, bonds. The black stuff, let's think of it as hard or rigid, better yet. And the orange stuff, let's think of it as soft and light. Okay, so that the structure can display a distinct resonance, mode. Okay, let's try to figure out what the equations of motion of this resonator are. So we have a pair of motion equations. One will deal with the angular momentum of the exterior shell. That's big I, big moment of inertia, big psi, big angle of rotation, and then these couple with the rotation and the moment of inertia of the inner mass. Okay, the coupling is done through the orange stuff, and the orange stuff, I'll assume that has some sort of torsional stiffness. I'll call eta, and then I have a torque that could be applied to the exterior shell. This torque is not like the torque I just mentioned. This torque is internal. It's not an exterior torque. This torque simply comes from these bonds in case they exert some torque over the shell. Well, these two equations can be made one by solving the second equation for small psi, and inject this result in the first equation. I end up with this equation here that describes a shell that has a restoring torque of stiffness eta psi. So whenever the outer shell tries to rotate, it perceives this restoring torque here. And then I add the internal torque of the blue bonds I call tau there. Okay, and the expression of eta star is a very usual expression, something that depends on the moment of inertia of the inner mass, the resonance frequency, and then the angular frequency of the field. Okay, well, asymmetric stress means externally applied torque, and there you have it. That's an externally applied torque. If tau is the internally applied torque coming from the blue bond, well, then it does not account for this torque applied by the inner mass, which I simply interpret as an externally applied torque of intensity eta star psi. And so in this structure, where in each mass I embed a resonator, I'll end up with asymmetric stresses. Almost, because I need still to check consistency as A goes to 0, that is, as the lattice becomes finer and finer, and while angular frequency is kept the same. That is, I'm looking at the homogenized, again, macroscopic behavior of this lattice. Okay, so let's check for consistency in this limit. Okay, well, torques are relevant if eta star psi, that is the external torque, is of the same order of magnitude as tau, the internal torque. In that case, eta star psi will perturb the equilibrium of internal torques. If this guy was much smaller or negligible compared to tau, then all of this is irrelevant and stresses will still be symmetric. So I need to make sure that these external torques are strong enough to modify the equilibrium of internal torques. And so I need eta star psi to be of the same order of magnitude as tau, but tau is proportional to A, size of the unit cell, that's the length of the arm, if you will, times K times A psi. And A psi is the displacement of this point here when the masses rotate by psi. The point here will be displaced by A psi times K, which is the stiffness of the spring, times, again, the length of the arm. So that's about A squared psi, given that K is a big O of 1. So not too small, not too large, times psi. And so that means that eta star will need to be of the order of A squared. Okay, so far so good. But I here in the numerator of eta psi is proportional to MA squared. M is the inner mass. And if the inner mass has a finite mass density, then M be proportional to A squared itself. That is the area of the unit cell. And so I is way too small. I is of the order of A4. And so I of the order of A4 will not allow me to have an eta star of the order of A squared unless the denominator does something funny. And the denominator does do something funny when omega approaches omega r, in which case the denominator approaches 0, and that 0 compensates for the smallness of I. Okay, and so this also requires that omega squared be of the same order as omega r squared, but the resonance frequency is of the order of eta over I, comes from here, eta over I. That's about resonance frequency squared. I mean, it's a characteristic frequency. I don't need to calculate the exact thing, just its order of magnitude. But I is A to the 4th, so divided by R, that's eta A to the -4. And eta is the torsional stiffness of the orange stuff, and that's about mu times A squared, where mu is shear modulus. And so I end up with a mu A to the -2 here. Last frequency, it's kept constant. And so mu must be of the order of A squared. That means that as I'm looking at the limit where the lattice becomes finer and finer, I assume that the orange stuff becomes softer and softer, so that its shear modulus is proportional to the size of the unit cell squared, or to the area of the unit cell. Okay, so under that assumption, well, stress will be asymmetric. Okay, so this is the material I end up with. I call it a polar metamaterial. And let's summarize what we did so far. So in the homogenization limit, that is A goes to 0, recall A is the size of a unit cell. Omega is kept constant. I shouldn't say constant, really. I should say kept of order 0. So omega is neither too high, it can be low. Omega being low is no problem, except that that means the resonance will be even of a lower frequency. But omega cannot be 0, for instance, because omega 0 kills the resonance completely, and I have no resonance to base my torques on. Okay, so omega non-zero, not too large. Such trusses with softly coated resonators, exactly in these ratios, will behave as an elastic solid with asymmetric stresses in the vicinity of the rotational resonance frequency omega r. Okay, we call such media polar metamaterials. I call them polar in reference to micropolar media, because in micropolar media or micropolar elasticity, Koster elasticity, usually stresses are asymmetric. But when they are asymmetric, that's because of these hyper stresses and micro rotation and all of that. But I have none of that here. So I was inspired by the name. I called it polar metamaterials. Hopefully the name is not too bad or prone to confusion. Anyway, in particular, exactly at the resonance frequency, well, the masses will not rotate at all, and the hexachiral lattice that you see on the left here will exhibit the effective constitutive law that we calculated. Okay, so this we calculated with a bad physical hypothesis, but we saved ourselves by assuming that there is a resonator resonating inside and compensating for these external torques. I hope that was clear enough. Okay, so this is unusual. I say unusual because, well, we have theorems, right? We have these theorems that say, well, a material in the limit, the homogenization limit should behave like a Cauchy medium where stress is symmetric. So what went wrong? Well, what went wrong is that mu approaches 0, and usually this violates one of the hypotheses of these mathematical theorems we have. Usually we have some lower bound on the elasticity tensor, and mu approaching 0 violates these bounds. And so that's one thing that went wrong, let's say. The other thing is that when mu goes to 0, well, the orange stuff is as if it wasn't there. So I could to leading order, that is, I could forget about it. And the unit cell ends up admitting up to 5 periodic motions with 0 strain energy. These motions are the translation of the unit cell. I have 2 of these. That's if I translate the full unit cell as a rigid body. I cannot rotate the unit cell because rotation of the unit cell as a whole is not a periodic motion. So I cannot rotate the unit cell as a whole. However, I can translate and rotate the inner mass. And so that gives me 5 periodic motions with 0 strain energy that I call 5 zero modes or 5 periodic zero modes. And that's another thing that went wrong. But still, these 2 facts are related. One is equivalent to the other. Okay, so now that we have these media, let's try to do something useful with them. I hope I'm doing well on timing. Okay.
Yes, you still have 20 minutes.
Okay, awesome. Thank you very much. Okay, so we started with this lattice here, this triangular lattice, and we built this hexachiral lattice. But still, these 2, I mean, if you look at the Lagrangian densities, you see they're very similar. One of them has B, the other has R. That's pretty much the only difference there is. And so maybe if somehow we rotate the B's to align with the R's, I can reinterpret one medium as the other. Let me re-say that. It looks like these 2 Lagrangians are related by a change of coordinates, where in one, I just rotate things somehow. This is not clear yet, how I rotate things. But seems as if just by applying a rotation somewhere, I can make one Lagrangian look exactly like the other. Okay, and so here's the change of coordinates I apply. I call big U the displacement here just so that I don't confuse myself. And I call the displacement here small u, big U, okay? And then X is the coordinate here, and big X is the coordinate there. And I assume that between the material element, big dx and small dx, there's some rotation, big R. And that means that the gradients of small u and of big U are related by this expression you see here. R prime is simply the transpose or the inverse of R. Let's say it's the transpose in my notations, and because R is a rotation, it happens also to be the inverse. Okay, and let me take R to be the rotation that rotates the B's into the R's. Note that the same rotation that rotates B3 into R3 also rotates B1 into R1 and B2 into R2. So one rotation will do. I don't need like 3 different rotations. That would have been bothersome. So the same rotation will do. And let's try to write this Lagrangian density small l in these new coordinates. Okay, so this is equal to gradient of big U R prime. And here I have R prime R, but R prime is the inverse of R. So RB is R, so that means that R prime R is B. And so I end up with this expression simply. Now I have B here and B there. So again, I can symmetrize the gradient. I don't need the full displacement gradient anymore. I only need the symmetric part. I cannot do that with small u, but if I write things with big U, I can. Remarkable, isn't it? Okay, and so this Lagrangian, look here and look there, these 2 Lagrangians are exactly the same, albeit I didn't obtain this Lagrangian. What I obtained is this guy, okay? So, but hey, this is isotropic anyway, right? It has C6 symmetry, so it's isotropic. Even if it wasn't isotropic, I'm happy with this connection between this lattice and that lattice. I'm very happy with that, to say that this hexachiral lattice is nothing but a triangular lattice rotated by some angle. Remember that this hexachiral lattice is resonant, okay? So it has resonators inside. It's not just your typical hexachiral lattice. Anyway, but this is isotropic again. I won. I have a change of coordinate that rewrites this Lagrangian as that Lagrangian. Okay. And such transform.
Am I the one being blocked, or is everyone blocked? Okay.
I lost it too.
Hussein? Hussein? I think his side is. Hussein? Hussein, can you hear me?
Yes, I can hear you very well. Yes.
Okay. So you can pick back up from where you stopped.
Okay, great. Okay, so I was saying that by molding solution fields, I can mold the solution fields by molding the structure. That is, by molding the underlying structure with this transformation, I'm guaranteed to have this connection between the displacement fields. And let's see how this makes something useful. This is called the transformation method. So the transformation method was introduced. Well, lately it's been introduced by Norris, Shuvalov, Milton, Brion, and Willis, but it can be traced back to the 1980s, actually. However, only recently we started talking about this transformation method for cloaking purposes. Recently, I mean like the years 2000 or something like that. Okay, so let's start with an original Lagrangian. What I'm doing here is redoing what I just did, only more general, okay? So original Lagrangian, I no longer assume a specific form for that. It's kinetic energy minus strain energy. Big A is the elasticity tensor now. I apply a change of variables of gradient F, and I allow now the displacements to not be aligned. So I allow for what we call a gauge, a linear gauge between small u and big U. Both G and F define the change of variables, okay? And then I define an image Lagrangian by this formula. That is, I transform the velocity field according to how the displacements are being transformed. And then I apply the chain rule with F here, like we did. I also divide by J, which is the determinant of F, because because big L and small l are densities, and so when I make a change of volume or of area, I need to account for that. So I also divide by J. Okay. So let's see what happens. Let's say that big F transforms this semi-infinite medium into this semi-infinite medium. Okay. Out there, you can see the grid is not distorted much. And so up here, small x is equal to big X. Well, what that means is small u is equal to big U. Well, really, it doesn't mean that small u is equal to big U. It only means so if G was identity. So forgive my mistake here. Let's assume that G is the identity. Okay. Otherwise, I'll confuse myself with these extra notations here. So let's say that G is identity. G is not there. Okay. And so in this region, small x is equal to big X, and the displacements match because of this relation where G again is identity. Okay. But in this region here, small x does not match big X because you can see that the grid is being deformed. So small x and big X do not match anymore. However, I still have this connection between small u and big U. Simply small u and big U do not correspond to the same location anymore, but to different locations, small x and big X. And the Lagrangian here is big L, and the Lagrangian there is small l. And again, big L and small l are related by change of coordinates. So whatever happens in one medium here will directly tell me and inform me about what happens in this medium there. Okay, so now let's talk about cloaking. Let's call this part of the medium the background. Let's call this part the cloak, and let's call this part the cloaked zone. Okay. Well, fields match over the background where small x is equal to big X, right? We just saw that. Well, that means that to an observer over there, it is impossible to distinguish the two media, because if you're sitting there, the fields will match with the cave, with the cloaked region, this cave here, and without it. And so there's no way for an observer located in the background to distinguish this from that. That means that the cave is invisible. That cave, as I created here using the transformation, it is what we call cloaked. Okay, great. The content of the cave does not matter. Why is that so? Because whatever you put here, that will only influence this sort of the scattering cross section of a line along a boundary. And so as long as what you put here is not like infinitely heavy or anything like that, its influence on the motion in the solid will be equivalent to perturbation localized along the surface, but that has zero influence anyway. And so whatever the content of the cave is, still these two media will exhibit the same motion in the background, and therefore to an observer in the background, this configuration and that configurations cannot be possibly distinguished. Okay. Well, the question that remains is, well, can you find a medium that fit this weird Lagrangian small l? Well, with this change of coordinates that I introduced a second ago, again, G is the identity. That means small u is equal to big U, although potentially at different locations. I allow for some extra freedom here. I say that the material elements are related through a rotation times some rescaling factor. This is what we call a conformal transformation. Okay. If we start with an original isotropic Lagrangian, like the one we obtained from the triangular lattice, for instance, well, then the image Lagrangian will correspond to what we obtained exactly with the hexachiral lattice with the resonators. And so, yes, I can find media that fit this small Lagrangian L. Mass density will need to be adjusted by this lambda squared factor, because again, I'm stretching or compressing the medium with the change of coordinate, and I need to account for that. Okay, let's see how we can apply that. I take the same transformation here, and then I take this region where I need this weird material, and well, I fit inside of it this hexagonal lattice with the resonator. This is a zoomed in version of that. Okay, and so this fills the space in the region of the cloak. The background, I can leave it as it is, because over there, well, the transformation is sort of the identity, and so I don't need to change the structure over there. I only need to change the structure inside the cloak domain. Okay, let's see what kind of results we get with that. So here we did simulations of scattering of the cave under incident pressure. So P here stands for pressure waves, and the incident wave will be an incident pressure wave. However, because of the coupling that happens along the boundaries, I'll have some shear component that is reflected or scattered, and that I'll call, I'll denote with the letter S. So here I have the pressure field incident at 0 degree, the shear field. Okay. Here I have the reference medium, that is the semi-infinite medium, no cave at all, just for reference. Then I have the flawed medium, where I carve a cave, but I don't change the material properties, sort of I do not coat the cave with a cloak. Then here I coat the cave with this cloak, exactly this one. And then here I coat the cave with an ideal cloak. The difference between the ideal cloak and the coarse cloak is that the coarse cloak really is the discrete structure that I put in the simulation, whereas for the ideal cloak, I put the continuum directly and put, well, finite elements over that. Whereas here for the coarsely cloaked, for the coarsely cloaked part, this is really the discrete structure coating the cave. Okay, so we see that with the flawed medium, I have a lot of scattering at different angles. I even have some Rayleigh scattering with P and S components. The coarse cloak improves the situation a lot. For instance, I suppress this Rayleigh scattering here and there, and I almost erase the scattering into S component. The ideal cloak does even better. In fact, it's very hard to distinguish this column D from this column A, and that points toward the success of this cloaking configuration. Okay, I can do things at 30 degrees. Again, here and there, I see small differences, whereas for the flawed cave, I see very scattering in several directions. You can see overall that the cloaking, cloak does better for the pressure wave rather than, or as compared to the shear wave. That's because the shear wave has a much smaller wavelength. And so to reach that ideal cloak situation, the step of the lattice must be even smaller for the shear wave as compared to the pressure wave. And so for equal step size for the lattice, it's natural to expect better performance for the P component rather than the S component. This is most visible here, for instance. Here, this scattering into S wave here, this shade sort of here, I do not see in the reference, but I see in the coarse cloak. But again, it's erased when I pass to the ideal cloak, where the fact that if I reduce the step size, I improve the cloaking behavior. Again, for P, even more than for S waves. Okay. Okay, so here's a second design where instead of a conformal transformation, I do a radially symmetric transformation. The problem with the conformal transformation is that it cannot create a cave in the bulk. Okay, to know why, well, you should look at some of these complex analysis theorems that deal with holomorphic functions over the complex plane. But anyway, with a smooth conformal mapping, I cannot create a cave inside the bulk of a medium while going to the identity beyond some horizon, beyond the region where the cloak is. Okay, well, it's not isotropic anymore. It becomes orthotropic. The material properties inside the cloak, that is, they become orthotropic. They're no longer isotropic, but that's fine. Everything we did still works just the same. It's just that it's a different class of symmetry, and we can fabricate a lattice similar to the one we observed a second ago. And this is the lattice fabricated with 3D printing. Now, this lattice is not resonant, but what we did to impose these body torques that are necessary for the breaking of stress symmetry, what we did is that we actually went in and controlled the rotations of the masses. So each mass here will move along a grid of 2 rails. You can see here on the bottom, this is one rail, and then when the mass moves, it reveals the other rail here. And so the mass can move in the XY plane, but cannot rotate at all. And like we saw at the beginning of this talk, constraining the rotation of the mass is equivalent to applying an external body torque, and that is enough to break stress symmetry. And so we did that. We fabricated this cloak. We only fabricated half of it, and I'm showing you the half of that half, so only a quarter. That's enough for, like, if we operate with symmetry, maybe half cloak is enough to show cloaking for a full cloak. Anyway. So here are the results. All of these are simulations, and what we're doing is that we're compressing vertically. Okay, so this is vertical compression, and you're looking at the displacement field. This is the reference, a lot of localization around the cave when we consider the flood configuration. If we cloak that with a discrete, what I call the coarse cloak with a discrete structure, things improve. We suppress this. This localization globally, at least. We create some finer localization, but hopefully, in the limit, all of these average away. Okay, and then the ideal cloak, where indeed this local localization was averaged away. We see very good agreement between the reference and the ideally cloaked configuration. Again, these are simulations, and here in the bottom right, you have the experimental results. The red dots are what you get for the flawed medium with the localization overall, and the blue dots are with the fabricated cloak, and then the black squares are the reference. And so overall, we see very good cloaking behavior, at least for compression. We did the same with shear loading, and we have similar results that I'll not be showing here. So with compression and shear and the symmetry that we have, we almost covered all ground for the behavior of the cloak. So that's rather promising. Okay. Okay, let me do a summary. How long do I have still? Maybe a couple minutes?
1 minute.
1 minute. Okay, so I'll do just the summary, and I'll pass to, maybe I'll move to conclusion. Okay, so conformal transformations maintain isotropy when we interpret them as changes of coordinates in the Lagrangian density. C6 symmetry is convenient. However, it's not really necessary. Chirality, however, is necessary. Well, you can see why chirality is necessary. A ray incident from the right will have to be bent upwards, whereas a ray incident from the left will have to be bent upwards again. But this here is to the left, this here is to the right. And this is why we need chirality. And indeed, if you look at this side of the cloak and at this side of the cloak, they have opposite chiralities. They are mirror images of one another. The last thing that I'd like to insist on is that a linear zero mode is also necessary. Here's why. The original structure has a zero mode that is an infinitesimal rotation, right? You rotate the whole thing, that's a zero mode. It costs zero energy. But then you can interpret this rotation in the new coordinates. And when you do that, the rotation does not go into another rotation. It goes into a genuine zero mode, a genuine mechanism where you have this unwinding motion. I hope you can see the difference between this configuration, where we have this unwinding of the bonds around the central mass. So we have unwinding, and at the same time, the whole structure expands. Whereas here, I have simple rotation, rigid body rotation of the whole. Now, this is a zero mode because during this unwinding motion, the masses do not change orientation. The mass is not rotating. Remember, the masses cannot rotate either because of these weird rails I added or because of the rotational resonance happening inside. And so this here is not a zero mode, but this unwinding motion is a zero mode. And so one zero mode is necessary, but be careful to which one is necessary. This one cannot be a zero mode for the reasons I presented. In fact, if this was a zero mode, stress would have been symmetric and everything will fail in that case. Okay. Well, we can do things with radially symmetric transformations. These will change isotropic behavior into orthotropic behavior. But really, the bottom line, I mean, the content is really the same. Rotational resonance breaks stress symmetry. Maybe that's a message I'd like to convey. And finally, I should say rotational resonance could break stress symmetry, to just be extra careful. Okay, so it can, it doesn't have to. And last, stress asymmetry does not call for full micropolar elasticity. That might be too rich for what we need to do. for cloaking, at least for elastic cloaking. Okay, let me pass to the conclusion. Maybe comment on nonlinearity for a second. So when you have a zero mode here, I drew a zero mode for a Kagome lattice. It's not the same lattice I used, but that's fine. When you operate a zero mode, the zero mode will only change things infinitesimally. But if you let the zero mode operate long enough, you'll change the full structure. And so you could move from, say, structure where stress is indeed asymmetric, but because of the strain you apply, you go to a structure where stress is no longer asymmetric. It can revert back to being symmetric. And so we could have, because of the deformation of the structure, we could have some sort of phase transition occurring at the same time. We've been studying this type of transformations in the case of these origami structures, and they do exhibit interesting elastic behaviors as well that go beyond maybe what Cauchy elasticity can reach. Okay, so let me conclude. Zero modes, periodic ones especially, can break typical symmetries of standard elasticity. I showed how, hopefully, how local modes can break stress symmetry. We can show that global zero modes can break the parity symmetry of the lattice. It's useful, at least as far as elastic cloaking can be useful. And last, it has exciting interactions with geometric nonlinearities that hopefully we could study more carefully in the future. I'd like to thank my collaborators from the University of Missouri, especially Dr. Huang and his group. We collaborated with a group from MIT with Professor Matusik, who helped us 3D print that cloaking structure I showed you with the intricate rail system. Thank you to Arthur Lebet from the École des Ponts and to Laurent Monas from INERIA, with whom I'm collaborating on these origami structures. I want to thank the sponsors that funded this research. And last, there are a few references that you could check out if you'd like to. Well, this has been very pleasant. Thank you very much for having the patience to listen to me. Thank you very much.
Thank you, Hussein. I would like to request everyone that if you have any questions, just type the text question. Okay, well, we have the first question from Patrick. Patrick, please ask your question.
Good morning.
Let me see. Good morning.
I have a problem of an understanding in the way you construct your Lagrangian, because you say that it will imply the symmetric part of the displacement gradient, which is not an objective transformation, which means if you have a change of geometry transforming R to B, you will not get the gradient as a measure of deformation. You will get a dilatation tensor or the grid Lagrange tensor. And how can you derive the Lagrangian with respect to a gradient to get a stress when you have change of transformation? I don't understand that you can do that.
Right, right. So if I understand the question is given this Lagrangian here, no. Okay, so given this Lagrangian here, if I understand the question, how do I justify the fact that stress sigma is the derivative of this Lagrangian density?
No, I say that the Lagrangian itself, the Lagrangian itself cannot be a Lagrangian.
Because it's not objective.
Exactly.
Well, that's fine. Objectivity, well, objectivity depends on what kind of extra constraints I have, sort of. So for instance, in that experimental demonstration, I added a rail system, and that rail system adds the ground. And when you have a system that is grounded, you don't expect objectivity to hold, because you've introduced a ground, you've introduced a particular frame of reference where the equation will take a very specific form. So I'm fine with objectivity breaking down in that case, because I know I've introduced something to bias this objectivity. Another way of looking at it with this resonant with this resonant structure here, it's that this behavior is only valid. Let me look at that here. This behavior is only valid, careful, where omega is equal approximately or equal exactly to the resonance frequency. And at a harmonic frequency, I don't really know how to formulate objectivity at all. Objectivity, I understand it as a rotation of the full medium. So that's sort of a zero frequency motion that I don't see at all in this case. So I agree with you. This constitutive law, sigma equals something times the full gradient of U, cannot be sort of universal. It will only work in very specific cases given some extra constraints from the outside, for instance, resonance in this case, or a ground, for instance. Was that clear?
Yes, but I disagree. So we need to discuss, because objectivity means not you make a difference between isotropy and objectivity. If you put rails in your microlattice, that's a material which loses isotropy, but I can rotate everything, the whole structure, add a rotation of the whole structure, and I should get a rotation of the stress that I will not get in your constitutive law. So,
right, but the ground is not part of the system. I do not consider the ground to be part of the system. Okay, so the ground is exterior to the system.
You can't. You can't move the structure if you don't move the rail in your lattice.
That's fine. Here's another way of putting it. Let's look. Do I have a motion equation somewhere here? It's enough to look at the motion equation where, let's look at this motion equation. For instance, I have divergence of C symmetric gradient plus F equals this guy. So suppose that I add a ground that penalizes displacement. So I'll replace body forces here with, for instance, negative KU. So if I put instead of F negative KU to account for a ground, I'm breaking objectivity, because now translations are no longer solutions to the motion equation, because I'm supposing that the ground is exterior to the system. Maybe that example helps understand what I'm saying. Is instead of body forces here, think of body forces as springs attached to the ground. So instead of F, I put negative KU, and there you go. I broke objectivity. Of course, that what I obtain cannot be a universal law, but for this particular system, where the ground is not part of what I'm looking at, the fact of not being objective is not really bothersome. Was that a bit clearer?
I'm still skeptical about that. I think there's probably a theoretical framework to adapt or to get the type of law that you want. I mean, but okay. What is interesting is to see the microstructure. So important, I agree with you, the importance is the microcolor.
Right. I'm not claiming that this will give us a universal law. I'm just saying that if I add a ground or a resonators, in a particular case, that will give me what I need. But the law cannot generalize to a universal law where I satisfy, say, objectivity, for instance.
Okay, do we have we have time for one question, or maybe two if it's a fast question. Do we have any more? Okay, maybe I have a quick question. In just now, you mentioned that you would like to replace your body force with something that connects you to an external, something outside of your system. But when you do that, wouldn't you have to extend your definition of the system to both the ground and what you consider your system, and then solve this equation for the whole, for the combined?
Well, I could, but I don't want to. It's like applying a boundary condition, right? You apply a boundary condition, you say along the boundary U is 0. Well, that breaks objectivity, but that's fine. I'm considering a boundary value problem. I do not need the boundary value problem to satisfy objectivity. In that sense, if I consider the boundaries, the boundary condition that is applied to the system as exterior to the system, I am breaking objectivity. In the same case here, if I apply ground, or if I connect my system to the ground like I did here with this system, I connected it to a system of rails. Well, here I could consider that the rails are part of the system, and that will only increase the complexity of my system. Or I could say the rails sort of apply a boundary condition to my system, and then I'm relieved because I don't need to deal with the full motion of the rails and all the complication that brings. So I consider that the rails sort of apply some sort of boundary conditions, and I take these conditions for granted.
Okay, so then it doesn't have to be a body force, right?
No, I was just giving that body force example as it was just an example. What we need here is a body torque, actually. So I need the masses to be free to translate, but I want to block their rotations. This is why I have this intricate rail system where the mass can actually slide in the XY plane, but cannot rotate at all. Okay, so what if I'm impeding mass rotation, what I'm doing is I'm applying a body torque. That body torque is understood where, as a body torque, of course, again, I could make the rail part of the system, but that will only increase the complexity of my system, and I'd rather not to.
Okay, thanks. Okay, so if there are no more questions, then let's thank our speaker again. And thank you, Hussein, for agreeing to do this so far away so early at your time, and for letting us record this session. And for everyone else, see you next week. Goodbye.
Thank you very much. Goodbye.